Okay, so welcome back again. And this time we are going to analyze the circuit which is shown on your screen. So as we can see that we have got this circuit using the CMOS technology, and we have this NMOS transistor here. We have this PMOS transistor here. There is this supply voltage VDD. We are applying an external input signal, which is sinusoidal in nature, is labeled as Vin. And in series with that, we have this resistor R1. V2 and V1 are the bias voltages to set the operating point of the circuit. And then we will have this external AC input that will be processed by the circuit. So processing means it will get amplified if we want to use this circuit as an amplifier. And here is the output of this circuit. So if we want to calculate the gain, if we are using this circuit as an amplifier, and if we want to calculate the gain, there are four types of gain we can determine. One is called as voltage gain, which is the ratio of output voltage divided by input voltage. Then there is this another gain, which is the ratio of output voltage divided by input current. And then there is output current divided by the input current. This is the third type of gain. So this is called as current gain. And finally, we will have output voltage, output current, in fact, divided by the input voltage. So this is called as voltage gain. Let me write here. This is called as current gain. This is called as transconductance gain, which is the ratio of output current divided by input voltage. And here is called as trans resistance, which is the ratio of output voltage divided by input current, trans resistance. So where is the input current and the output current? We know that this is your output voltage, this is your input voltage. So here, the current that is supplied by the Vin is I in, which is actually flowing through the resistor R1 and here. And when you have the external loads, so the output current that is delivered by this circuit can be labeled like this. So this is an output current, which will eventually flow through the load when you connect the external load to the circuit. Now, there are three combinations in which the circuit of BJT or MOSFETs can be biased. So those combinations are called as common gate in terms of CMOS, common drain, and common source. So if I ask you to identify in which configuration this circuit is biased, so we can see that your input is applied to the source pin of this transistor. Here is the drain pin of this transistor, and here is the gate pin of this transistor. So when doing an AC analysis, we see that this input is applied to the source pin here, and the output is taken from the drain pin. So the gate pin is common to the output and the input. So therefore, this particular circuit is biased in common gate configuration. Okay. Now the next step is to draw the small signal model in order to evaluate all these four types of gains. So we will draw that right now. So what we do here, before that we can simply label here. So we see that this transistor M1, let's say, and this is the transistor M2. Let me use the pen here. This is M1. This is your transistor M2. So when you do the small signal analysis, you want to draw the AC equivalent circuit for this circuit. So M1 is acting as a amplifying device and M2 is acting as a load, active load to this M1. So here we model the M1 as a dependent current source, which has the value of GM times VGS1. So VGS is the voltage right over here. This is VGS1, okay, for the M1. And this transistor is, the current is flowing, this ID current, ID, which is equal to GM times VGS1, specifically GM1 times VGS1 is flowing from drain to source pin. So here is that current. Okay. Now from the source pin right here, here is your source pin, this is your drain pin, and this is your gate pin. Okay. So from the source pin, you have this external input that you are connecting. So here you have V in that gives rise to I in, which flows through resistor R. And this is your source pin right over here. Okay, now you, when you do the AC analysis, the DC voltage sources into the circuit are short circuited. It means they are connected to the ground. So this goes to ground. V1 and V2 are also bias voltages. So they are DC voltage sources. So they are also effectively connected to the ground in order to perform the AC analysis or drawing the small signal model. So we see that the gate of transistor M1 is right here, that is connected to the ground, and here is the drop, that positive voltage drop if we take, that is VGS1, which is the voltage drop across the gate and the source pin of the transistor. Okay, so that is all right over here. Now, um, if we take into account the channel length modulation effect, so you have got the resistance from drain to source, that is called as output resistance R1 of transistor M1. So we can see that that is connected between drain and the source. So we are likely to draw that resistance right over here from drain to source R1. Okay. And here is your drain 1, comma drain 2. So drain 2 is here of this transistor M2, and this is source 2, which is connected to the ground. And here also, since M2 is acting as active load, it will offer its own output resistance as a load resistance to M1. So here is your RO2, which is connected between drain 2 with respect to ground. So we can draw here that this resistance R2, RO2 is connected right here. And then here is your output, V output right here at the intersection of drain 1, at the junction of drain 1 and drain 2. So here is our junction. We are drawing it. So that is R2. So we are done with our small signal model. So we can see that right here, this is an input side. This is an input side of the circuit, and this is an output side of the circuit, right? So to the input side of the circuit, we can write some equation to understand what the VGS value is. So here you can see that by applying the KVL, we see that right over here, we will see that the Kirchhoff's voltage law, KVL, gives us V in minus I in times R minus VGS1 is equal to 0. Therefore, we say that VGS1 is equal to V in minus I times R. So that's our KVL, because we want to understand what is the value of VGS1. Okay, now you have got this circuit, and then there is this current flowing I in, which is flowing through R, and this current is your ID that is coming here. So at this junction, we can see that through the KCL, here we say that apply KCL, Kirchhoff's current law. we see that I in is equal to minus ID. So both currents are incoming. So sum of the incoming currents are zero. So I in will be equal to minus of ID, and which ID is your GM1 times VGS1. So we'll see that this is GM1 times VGS1. So now this current is basically the sum of this current I, let's call it like I, which is flowing through this resistor R01, and then it is flowing and it is coming right here. So we'll call it IO. In fact, our IO is basically outgoing current, which is the sum of two incoming current, I in plus ID, right? So we can see that I in is V in divided by R, Ohm's law, plus ID, and ID is your GM times VGS1. So further simplifying this, we get the value of GM, and VGS1 is this one here. So we see that V in minus I in times R. We keep on simplifying it. V in divided by R plus GMV in minus I in again is V in by R multiplied by R. So R gets cancelled here. Here we can see that. And V in minus V in is equal to 0 multiplied by GM is 0. So this whole term is getting 0. And therefore we would write, let me write here, IO is actually V in by. So the output current that is getting delivered to the load. Now the load is RO2 is V in by R. Now V out is actually IO times RO2. Therefore, V in divided by R into RO2 is your V out. And the first gain V out divided by V in, just we are taking the V in to the left side of this equation, is equal to RO2 divided by R. So that's your voltage gain of this circuit if you want to use it as a voltage amplifier. And the gain is set clearly by the output resistance of transistor M2 divided by the source resistance of the signal that you are applying to be amplified. So that's how you see, using the equivalent model, we are good to calculate the expression or determine the expression for the voltage gain. How about I want to get the expression for V out divided by I in. So I will write it here, V out divided by I in, which is trans resistance or trans impedance amplifier. Now, if I use the capacitors into the AC model, then I will have to use the word trans impedance. In this, we will write V out. We know that it is output current divided by, multiplied by the output resistance, that is RO2. And I in is your input voltage divided by an input resistance. So we just plug in those values, that is IO times RO2 divided by V in divided by R. And we know that the value of IO is V in divided by R. We have solved that. So it is V in divided by R multiplied by RO2 divided by V in divided by R. So these two terms get cancelled. Finally, we are left with RO2. So V out over I in, here we write V out over R in. Now V out over I in actually. I in is RO2. So this is the RO2, that is your resistive gain, that is the trans resistance gain. Okay, so we are good so far. Now let me write the expression for IO divided by I in. So here IO divided by I in is we want to determine. So we know that DIO is your V in divided by R. We just say that this is the value of IO. Remember this. And your I in is V in divided by R, right? So I in is right over here. So we know that this is, in fact, uh, this value, this is I in actually. So we know that this is the ratio of 1. So the current gain is 1 in this amplifier. The voltage gain is RO2 divided by R. So RO2 generally is very, very greater than R. So voltage gain V out over V in, therefore is very, very greater than 1. And the current gain here is exactly equal to 1, and the transimpedance gain or transresistance gain is also very, very greater than 1 because it is RO2. Now finally we can talk about this gain. Right, so finally the transconductance gain, which is the ratio of I out divided by V in, can be written as your I out is V in divided by R, and we know that V in is this voltage right here. So we will write therefore I out divided by V in, which is actually V in divided by R divided by V in. So that comes out to be V in by R into 1 over V in. So it is 1 over R. So obviously, this transconductance gain is set by this resistance, and it is equal to the reciprocal of the value of this resistance. So hope you found this video useful, in which we derived all 4 types of gains, that is voltage gain, current gain, transresistance gain, and the transconductance gain for the circuit biased in the common gate mode, common gate configuration using the CMOS circuit design. And if you found this video useful, share it with others, comment, like, subscribe, and stay tuned for more engaging contents like this. And specifically, if you found any mistake in the derivations or you have some comments, so don't forget to write that in the comment section. Till then, wish you happy learning.